the real-time digital signal processing lab class for spring 2014. This is lecture 7, part 2 on interpolation and pulse shaping. So in part 1, we had talked about several things: discrete to continuous time conversion in the application context of digital to analog conversion, but it doesn't have to end there. Interpolation, which we talked a little bit about in general, how you do this in discrete time as well, how you make an image bigger and fill in the new pixels. We talked about pulse shapes to perform the interpolation. We've talked about rectangular, triangular pulses in particular. So rectangular was sample and hold, and triangular was linear interpolation. Today we'll start with the sync pulse, we'll do raise cosine, and we'll do the demo and wrap up. Any questions from last time? Okay, fire them away, as per usual, as they occur to you. So this was the context for the first part. We talked about, in particular, digital to analog conversion as an application of interpolation, and in particular, it was in the block here doing discrete time to continuous time conversion. And whatever artifacts we introduce in this step, we will clean up with an analog low-pass filter that follows it. And as I mentioned last time, there's a design trade-off. The more work you do in discrete time, the less work you have to do in continuous time, and vice versa. So it's a design trade-off and a design decision. All right, so again, our goal here is to take some discrete time signal, and it's also digital. It is quantized in amplitude, and we'd like to produce a continuous time waveform that looks like what we might have started with in analog to digital conversion. But our conversion is only good to what range of frequencies? Fs over 2. So when we sample, we're going to capture frequencies up to half the sampling rate. That means that when we're in discrete time and we want to reconstruct, the best that we can do is frequencies up to half the sampling rate. Now in discrete time, we've abstracted away the sampling rate that we would have used originally, but that's often kept in the designer's head in the program. So we have some flexibility in how to choose the sampling rate, Fs here. But whatever sampling rate we choose for Fs in the discrete time to continuous time conversion step, it means that we really can only guarantee reconstruction up to half the sampling rate. Any frequency content above half the sampling rate are artifacts, again, from this conversion step from discrete time to continuous time. So again, that's a review from part 1. Also in part 1, we talked about the general form of interpolation for discrete time to continuous time conversion. And as you might guess, this general form also works in discrete time for discrete time interpolation, and it does. So here's the idea for discrete time to continuous time conversion. I have a discrete time signal y of n, and I want to create an approximation in continuous time analog domain, and we can do this through filtering. It's convolution, and it's a little bit unusual in that the convolutions involving a placeholder variable in discrete time and an outer variable in continuous time. So as I mentioned last time, this was mixed signal filtering or processing, and by mixed here we're referring to mixing time domains. We're mixing both discrete time y of n and continuous time p of little t minus capital T s little n. So I have both continuous time and discrete time variables in the same operation. Now, this is how I go. This is a linear system view of how I go from discrete time to continuous time. I can take the same view and go from discrete time to discrete time. So I can use the same view to interpolate in discrete time. I still use pulse shapes, P. The difference is now my outer variable of convolution would be discrete time. So what we do in discrete time cases, we'll upsample, add a bunch of zeros after each sample that we have, and then we run it through an interpolation filter to smooth out the result. And we'll do plenty of examples later in, I guess it's next week, and we talk more about pulse shaping and communication systems. Okay, so, but anyway, so this particular interpolation is discrete time to continuous time, but it also applies from discrete time to discrete time. And it's another filtering operation. Okay. So far we've talked about rectangular pulses and triangular pulses, and then today we'll talk about sinc, truncated sinc, and raised cosine. Okay, so again, this is a filtering step. Each of these pulse shapes really is the impulse response of a filter. And in each case, each of these impulse responses has what frequency selectivity in the Fourier domain? Is there low pass, high pass, band pass? Low pass, right? And that comes from why? Why do we have low pass pulse shapes? Why do we have low pass pulse shapes? So this is the discrete time to continuous time step. So it is true that we want to reduce the amount of artificial frequencies at or above half the sampling rate, but we're going to have analog low pass filter to clean that up. This is a reconstruction step from discrete time to continuous time. So why low pass? As opposed to high pass. So you're partially right that we don't want to introduce too many high frequency artifacts. That's true. But why else low pass? Go ahead. Right, remember from the sampling theorem, when we derived that in lecture 4, the ideal reconstruction is from an ideal low-pass filter, provided that we have obeyed the sampling theorem. Right, so if we have an ideal low-pass signal that we're sampling, a band-limited or baseband signal, so if I start with a signal that I'm sampling, here's the Fourier domain, and it is ideally band-limited, again, on idealism, right? So if that's our starting point, and we sample that, right? So if we sample this, we get the replicas. So we get the baseband comes through, and then we get offsets of the same spectrum, the same shape, at integer multiples of the sampling rate. So this point is still F max. That center point is the sampling rate. This center point is 2 times the sampling rate. Right? So we get these replicas, and the offsets are integer multiples of the sampling rate. So this is X sampled of F. So to reconstruct, provided we've obeyed the sampling theorem, I need to put in a low-pass filter some days are stranger than others. Okay. We're going to put in a low-pass filter to pull an ideal low-pass filter. We can talk, it's all ideal in this discussion so far. So I want to have a low-pass filter that extracts the baseband component and rejects the rest. Now, of course, in practice, we can't do this. In practice, you really have a filter that will roll off from passband to stopband, and the stopband won't be exactly 0. So we will always have some aliasing, or some, in this case, some imaging, some frequencies that we'll get through. So this is the sampling side. So we will still get some aliasing on the sampling side. And then for reconstruction, we're going to apply this low-pass filter. And so even in the ideal case, we're not going to have any influence from these replicas, but in practice we will. So if we obey, so let me rephrase that. So if I obey the sampling theorem, that the sampling rate is greater than 2F max, in this ideal case, I don't have any aliasing because I have an ideally band-limited signal. When I do the reconstruction, if I reconstruct with an ideal low-pass filter, I also don't have any distortion. I have exactly what I started with. Provided that I obey the sampling theorem, it gives me enough room between replicas to insert my low-pass filter, in theory, right, in idealism. Oversampling helps us, because oversampling allows this gap to be wider. Makes it easier to put in the ideal low-pass, a practical low-pass filter. So oversampling is a good thing. It makes it easier to reconstruct. Okay. So that explains why this pulse shape has low frequency as a low-pass frequency selectivity. The ideal interpolator would be a two-sided sink in the time domain as our pulse shape, which would correspond to the ideal low-pass filter in the frequency domain. Here's our ideal low-pass filter. But again, we can't build that, but we can build instead a truncated sink. We can have an impulse response. It's a sink for a finite amount of time, and that's what we'll do. In the communication systems that we design. But all three are useful here. Rectangular pulse shapes, triangular pulse shapes, and truncated sinks. All are useful in practice. Okay, so last time we went through the frequency responses of rectangular pulse and triangular pulse. And again, we saw that here is, again, this is for this is a rectangular pulse in the time domain. We get a sink in the Fourier domain, which is low pass. That's for zero order hold or rectangular pulse for our interpolation. For triangular pulse, in the time domain, it's a triangle. And in the Fourier domain, it's the sink squared. So it's still a low pass. Now, a tougher question, what's the stop band attenuation for this response? Give that a thought for a second. What's the stop band attenuation if the pulse shape's rectangular pulse? 13.5 dB. Very good. So we've talked about this. So if this is my frequency response, right, this is my Fourier transform of the rectangular pulse. It has a null bandwidth of, what's it? 1 over TS, and the stop band attenuation is 13.5 dB. Go ahead. I haven't derived that in a while. That's from memory. But every time that we've done this, every time you've plotted the magnitude response of the averaging filter, no matter what length it was, that stop band attenuation was always 13.5 dB.
That's from the previous.
That's right. That's from previous lectures. That's right. And homework experience.
Yes.
Very good. All right. So that, and there's a midterm in there too. We did some of this. Yeah. Okay. So here, anyway, so 13.5 dB here. Now the question is, for the triangular pulse, you can view the triangular pulse as coming from the rectangular pulse convolved with itself. Okay, so that would be like, so to get this triangular pulse, it's equivalent to filtering with the rectangular pulse and then filtering with the rectangular pulse again. Right, that's the equivalent of that's what we're doing here. Or you can say, well, if I have, again, two LTI systems in cascade, the impulse response is convolved. So I can write this as a composite filter. That's the wider triangle. All right, these are equivalent. I'm in continuous time here. They're equivalent. All right, so now what's the stop band attenuation for this filter? 27 dB would be correct. Okay, so if you're, now remember in the Fourier domain, so how do we get that? So in the Fourier domain, the magnitude, if I look at what happens in the Fourier domain, I have two LTI systems in cascade. It means that their frequency responses multiply. Right? So we talk about capital Y of F is H1 of F H2 of f, x of f. Convolution in the time domain becomes a product in the Fourier domain. So the magnitude responses, so that's, cascade of 2 LTI filters, H1 and H2. Magnitude response, right? The magnitude of a product is a product of the magnitudes. So if I multiply these two, it means that whatever in the stop band is going to multiply by itself in the stop band. And if I take the log of that, if I take the log of a product, what happens? What's the form there? So I take a log. You add them. So I take the log of A times B, log of A plus log of B. Right. So that means that if I have 13 dB stop band attenuation, sorry for the change of colors. I've lost the red on the palette. It's pretty close. So if I have 13 dB in H1 for stop band attenuation, I have 13.5 dB of stop band attenuation in H1, 13.5 dB of stop band attenuation in H2. It means that, remember, dB is in log scale. So their dBs are their stop bands will add. Stop band attenuations will add. This multiplication is in the linear units, and in dB it's a sum, right? Because of this identity for the logarithm. All right, so it's a little better low-pass filter. The stop band attenuation is 27 dB. It's better. What about the null bandwidth? I'm multiplying these two together in the time domain. What happens to the null bandwidth? I hear 1 over 2 TS. Remember, this is just multiplication. There's no convolution in the Fourier domain. Still 1 over TS, not squared. Not squared. So I'm thinking about an ideal low-pass filter in the time domain. Just ideal for convenience. And I multiply it by another one that looks the same. All right, if I multiply these two together, I still stay, and here's the null bandwidth, F naught. All right, so the null bandwidths aren't going to change. Now, I guess, and now if I want to fill in the real detail, since it's a sink, it's going to really look like this. Okay. Now, if I multiply the two the magnitude responses here that I've shaded in black, the null bandwidth hasn't changed. Pass band is still the pass band, the stop band is still the stop band. 1 multiplied by 1 is still 1, so my pass band is still 1 in linear units and 0 in dB. But the nice thing about this particular filter is the stop band attenuation has increased to 27 dB. Still not a great filter. We've designed, filters with 40 dB, the demos with 60, 80, 100. So 27 isn't a lot, but it's better than 13.5. All right, so let's get on to the sync pulse. Okay, so here's the sync pulse. So for the sync pulse, again, it's two-sided sync in the time domain. Overall time from minus infinity to infinity. And the Fourier transform is an ideal low-pass filter. It's a rectangular pulse in the Fourier domain. Okay, ideal low-pass filter it's an ideal low-pass filter, so the Fourier transform is just a rectangular pulse. This sink is non-causal, so we're going to get, the phase will be 0. In this case, phase response. Okay, so a few observations. So in the time domain, we get infinite overlap with other adjacent pulses because the sink pulse is infinite in duration. So it's going to overlap with all the other pulses used in reconstruction or interpolation for discrete time to continuous time conversion. However, in the Fourier domain, we're finally band limited, which was not the case for the rectangular pulse or the triangular pulse. But again, this is we can't build it, so it's nice to have something that's band limited in the Fourier domain, but it's infinite in extent in the time domain. Right. So that's nice, but we know it's a starting point because this is the filter we would like to use for reconstruction based on what we know from sampling and the sampling theorem. Okay, so we can't interpolate with an infinite extent pulse in time. So what can we do instead? Like I said, we can truncate the sink pulse by multiplying it by a rectangular pulse, so limit the width of the sink pulse. Now, if we do that, if I multiply in the time domain, it means I convolve in the Fourier domain. So now in the Fourier domain, I'm convolving the Fourier transform of the sink pulse, which is the rectangular pulse, with the Fourier transform of the rectangular pulse, which is the sink pulse. Say that fast, right? 10 times. So we're going to convolve with the, so we're convolving the rectangular pulse with the sink pulse in the Fourier domain. So I don't know, the answer is pretty complicated. What I do know is that this ideal low-pass filter will now smear due to that convolution. And we'll get something that looks more common. It's going to have a pass band, a transition band, and a stop band. The longer the rectangular pulse, the more of the energy we keep in the time domain, and the more the result in the Fourier domain looks like the ideal case. All right, now that's the sink pulse, which is the ideal reconstruction filter, but we can't use it in practice. We cannot implement the ideal one, but we can implement the truncated one. Now, one of the drawbacks of the truncated, even the truncated sink has a drawback, and that is in the time domain it does not die out very quickly. So in the time domain, the sink takes its time, slowly going to 0 in amplitude. Right, so slowly goes to 0. And so if we truncate the sink pulse, say to, for example, from here to here, we lose a lot of energy. There's a lot of energy in these tails because the tails here go off to infinity to the right and minus infinity to the left. So what we can do instead is do a variation of the sink, which is called the raised cosine, which will have the amplitude die out faster as time goes to infinity. So we don't lose as much energy when we truncate. And this is the raised cosine. So we're using this next week in lab, starting on Monday. This is the pulse shape we like to use in communication systems, and you'll see why for some nice reasons in this slide and next. So the formula for the raised cosine is based on the sink, and then we add a scaling factor to it. And you'll notice in the scaling factor, in the denominator, there's a lot of terms here. So just read it through. I have cosine, so in the numerator, cosine 2 pi alpha, so we have some parameter alpha. Capital W, which was the ideal bandwidth, the bandwidth of the ideal filter, which is half the sampling rate. And T, little t for time. In the denominator, we have 1 minus 16 alpha squared, W squared, and T squared. What you see here is in the denominator, we now have this dampening term that's T squared. So it means that now I'm going to have the amplitude die out faster as time goes to infinity. It's now going to die out not at just the rate of T from the sink term, but now T times T squared. So now the die out, or the pace of decay to 0, will be at the rate of 1 over T cubed. Much faster decay. And we'll look at the impact on the frequency response on the next slide. So again, we have an ideal low-pass filter response, a two-sided sink, And we attenuate this by another term that's proportional to 1 over t squared. Go ahead.
There's no Fourier transform for that.
There is. Next slide.
Oh, there is?
Yeah, someone else worked it out. We're going to look this one up, right? Why reinvent the wheel? All right. So if you look at the time domain response, the sink you can kind of see. So let's go back to the parameters. So again, capital W is the bandwidth of the ideal low-pass response. This is 1/2 the sampling rate. Alpha is a roll-off factor. It's from 0 to 1 inclusive. When alpha is 0, look at what happens. So when alpha is 0, what happens to the cosine? It's 1. And what happens to the denominator? When alpha is 0, 1. Okay, so when alpha is 0, we go back to only the sink. There's no impact now from the multiplicative attenuation term on the right. Now, as alpha increases beyond 0, we get more and more influence from the attenuation term. Now, I get 0 crossings, and we know this from the sink. The 0 crossings haven't changed. There's still, if you look at this, there's still a plus or minus integer multiples of the sampling time, except at 0. At 0, we have the maximum value of 1. Okay, now if you look at what happens in the time domain, as alpha, so here's alpha 0, so it's fine. Alpha 0 is the one with the largest, or the largest valley in absolute value terms. If we start increasing alpha, you'll notice that the depth of the valley decreases with alpha, with increasing alpha. Okay. So that's good. That means that when we truncate the raised cosine, we don't lose much energy if alpha is 1. We lose a lot of energy when alpha is 0. There's a handout in the reader for this, which has a lot of this information in the course reader. It's handout G. All right, let's look at what happens in the. Although I should point out, there's one more set of 0 crossings when alpha is 1. You'll see that here. There it is. So there's an additional set of 0 crossings at 3/2 TS and 5/2 TS and so forth. We don't put this to much use really in practice, but it's just, I suppose, interesting. Here's the impact in the Fourier domain. In the Fourier domain, it should look pretty familiar. It looks like a filter response, right, with a pass band, transition band, and stop band. This is the this would be the untruncated form. We haven't truncated yet. We're just doing the the two-sided case for now. All right. So again, this is a pulse shape we use in communication systems. Very common pulse shape. The bandwidth. So what's the impact of the roll-off factor in the frequency domain? It increases the bandwidth. So when alpha is 0, I'm back to just the sink, and my bandwidth is simply capital W. Right? So the bandwidth increases by a factor of 1 plus alpha. Not too bad. So it's a nice trade-off. A little bit of extra bandwidth for a really nice, a much better situation for energy loss when we truncate. Okay, so if we look at the frequency response, the formula is here. It's a nice formula. It's a beautiful formula. Okay, so we, certainly we need to use the formula, but the raised cosine is a built-in function in MATLAB, so we use that. But you're welcome to program it from scratch if you want. So if we look at the frequency response, we have 3 parts to it. We have the pass band. It's constant. We have the transition band, a little more complicated formula, and we have the stop band. Now remember, this is the ideal case, two-sided in time. In practice, we're going to truncate, so we will see energy in the stop band, or some non-zero values in the stop band. How does this look in terms of a picture? Well, it should look familiar. So the rectangular case, the ideal when alpha is 0, nice rectangular pulse. For the frequency response, when alpha is 0, what we expect to see, it's a Fourier transform of the sink. Alpha of 1/2, the bandwidth increases by 1 plus alpha, which would be 3/2 in this case. The plot here is normalized. It's F over capital W, the bandwidth. And when alpha is 1, we now have a bandwidth of 2, or 2 times capital W. So we have twice the bandwidth. For when alpha is 1, it's twice the bandwidth that we need versus alpha equals 0. So it uses up a little more spectrum, but the good news is it decays really, really fast in the time domain. We can make a short pulse out of it more easily without lots of energy. Okay, so again, we have a pass band. So we have a pass band, we have a transition band, we have a stop band. And then between the pass band and stop band would be the transition band. Okay. So there's your raised cosine. All right, so let's go on to the demo. It's the demo we've run before. We're going to do sampling and interpolation. We'll sample at different rates and use 3 different pulse shapes to reconstruct. We've done this before, but now it's nice to go back and look at a familiar demo with a little bit extra coverage of the material that's in the reconstruction part. Okay, again, demos from DSP first, as mentioned on the slides. So we'll do what we did last time. We'll do a cosine, single frequency, 600 hertz, and a constant phase offset of pi over 3. So we know we want to sample it. If this were two-sided, we would want to sample more than 1200 hertz, right? 2 times 600. The reality is, we know it's a finite length signal, so we know there's a little more bandwidth to this. Maybe an extra 10 hertz, something like that. So we really want to sample it more than, say, 1220. And we do. So we're going to sample at 1250. Here's the signal in time domain prior to sampling. All this is all done in MATLAB originally. So we have slightly more than 2 samples per period of the cosine. You see them here. Again, they're missing. This one at 0 is missing, but it's really there. So there's a sample there. So I can connect the dots, right, the amplitudes of the samples that I know, using zero-order hold, and I get sort of a staircase approximation. And it doesn't look all that good, honestly, compared, at least in the time domain. But it does capture the significant frequency content, which is reflected in the zero crossings. So for a sinusoid, we want 2 zero crossings per period of the cosine or sine, and we get that. They don't occur in the right locations, but they occur with the right frequency or the right rate. Now, so in practice, we could clean this up with an analog low-pass filter, and that would round out the edges, at least for any frequencies at or above half the sampling rate, but we'd still have some harmonics that would get through. Okay, so in this case, this critical sampling, actually we wouldn't have any harm. So in this case, the frequency was 600 hertz of the cosine. The sampling rate was 1250. That means the cosine has harmonics at 1200, 1800, and so forth. So actually it's even. That's right, it's a square wave, not a cosine. So it's a square wave with harmonics at multiples of 600. So the analog low-pass filter, if it cuts off at 625, is going to remove all the harmonics. And we'll get a very smooth looking cosine after we pass this through an analog low pass filter. Take the same samples, reconstruct with a triangular pulse, which is linear interpolation. So now I'm connecting the dots with the lines. Again, we've seen this before. It's sawtooth approximation. Captures the zero crossings, at least in frequency, but not location. Doesn't look much like the original. But again, if we pass this through an an analog low-pass filter with a stop band at half the sampling rate, it will clean up, and we'll get back a nice-looking sine wave. But not the exact one that we started with, but something that would be lower in amplitude. It would basically take this sawtooth waveform, filter it, get rid of all the harmonics, and we would get a sinusoid, but it would be offset from the original one and at a slightly different amplitude. So again, it's an example of if I don't do much work on the discrete time to continuous time conversion stuff, I have to do more work on the analog low-pass filter that follows it. All right, now if we do the reconstruction with a truncated sink, and this truncated sink here will be 4 sampling periods wide. So here is one width, one of those sink pulses. So again, 4 sampling periods wide. At least it's better at tracking the time domain waveform, but it still doesn't hit the zero crossings in the right locations, but it does capture the frequency of the zero crossings. So now let's talk about oversampling. All right, so that was sampling at just above 2f max. If we sample at 4f max, we'll do 2f max. Why not? So now we'll sample 2450, reconstruct with a rectangular pulse, zero order hold. It's better. I'm closer to the zero crossing locations, much closer, but not exactly a cosine. But if I follow this with analog low pass filter, it will look a lot better. We get very close to the original cosine. Let's do linear interpolation at 2x oversampling. Okay, we're hitting the zero crossings really well. That's good. And we get these jagged corners, again, corresponding to higher frequency content, harmonics. Lastly, truncated sink. And now it's looking pretty good. So 2x oversampling with the right pulse shape, truncated sink, looks really good. We're missing a little bit here on the valleys and the peaks. Zero crossings are at the right locations, at least from what we can see. But we're not getting quite high enough on the... I'm sorry, it's the other way around. Sorry. It's going too high and too low. That's it. Right. So the reconstruction is a solid line. It's overshooting the valleys and the peaks. But not bad. So 2x makes it better. We're tracking the time domain waveform better. So let's do 4x oversampling. So 4x, zero order hold, pretty good. It's pretty good. Oversampling has made this look pretty good. And again, if we follow this with an analog low pass filter, we'll get rid of the harmonics above, in this case, 2400 hertz. So we still will keep the first few harmonics and get rid of the rest. We get a smoother result. Linear interpolation at 4x oversampling, pretty good. A little bit of miss in the peaks and the valleys, pretty good at 4x oversampling. And lastly, the truncated sink at 4x oversampling, pretty amazing. A little bit of miss in the beginning, and that's due to the group delay of the filter. Very good. After that, man, it's right on. It's just tracking. Okay, so here again, this oversampling is a good thing for signal quality. The questions on this? That's exciting. go ahead and just wrap up for conclusion. So and it's kind of what we've talked about so far. So discrete to continuous time conversion involves interpolating between known discrete time samples y of n using a pulse-shaped P of t. Common pulse shapes, rectangular pulse for really sample and hold. It's a type of sample and hold interpolation. Triangular pulse for linear interpolation. Sync for the optimal, this is two-sided sync for the optimal or best we can do for band-limited linear interpolation, but it's impractical. And then truncated sync or truncated raised cosine for practical band-limited interpolation. Again, the raised cosine is a generalization of the sync. The truncation in the time domain causes smearing in the frequency domain, but again, we control that in the raised cosine by the alpha parameter, the roll-off parameter. Okay, that will end lecture 7, part 2. So thank you for joining us on the video.